Hi, I'm Tracy Cook, and I am the Director of Conservation and Curation here at the Huntsville Botanical Garden. And this is
Peter Hanna. I'm a volunteer here.
And we are going to be presenting today a case study using GIS to manage a botanical garden. So we'll be defining our problems, seeking solutions, and then showing you a little bit about some of the solutions we found in our improvements and methods. So now we'd like to introduce you to our garden.
The 112-acre Huntsville Botanical Garden is open year-round and contains a diverse ecosystem of meadows, upland and bottomland forest, and wetlands, as well as a variety of specialty gardens and native plant collections. The Matthews Nature Trail contains the largest accredited trillium collection in the U.S., and the Anderson Education Center is home to the nation's largest open-air butterfly house. A 501c3 nonprofit organization, the garden is a member of the American Public Gardens Association, the National American Plant Collections Consortium, and the American Horticultural Society, as well as an ARBNet-accredited arboretum.
In 2011, when I joined the garden, our plant records were recorded in Microsoft Access and mapped using time-consuming ground survey techniques and paper field data forms, which were meticulously drawn into AutoCAD at a 0-0 reference scale by Mike Gibson, who was then our curator. Accuracy checks were a combination of triangulation and cross-referencing aerial photographs that were generously donated but not ortho-rectified or mosaicked. There was a wealth of information in these documents, but sharing that information was next to impossible because few people had the licensing to view the CAD drawings. Interpretation of the plant records and dedications data required Mike, or later me, to look up and reconcile each of these documents. Two additional confounding factors were that the Access file was set up as a series of unrelated spreadsheets and used as a proprietary series of codes and abbreviations that took some familiarity to decipher. Add in the common problem of inconsistency of data format, and we had a very large data set with 30 years of information that was impossible to query effectively. Also, many volunteers and staff make changes to the landscape daily at Huntsville Botanical Garden, and because of the time-consuming nature of the mapping workflow, there was often a substantial time lag in getting survey data out of the field, integrated into the map, which resulted in a map that was always out of date. We knew we needed a better way to manage our data, and that GIS was a technology that could help.
What Tracy just described can be boiled down into these specific impacts: usability and accessibility. The data are not accessible to the people who needed information from them. The spatial and tabular data are disconnected. The G is separate from the I, difficult to query and analyze and model. Data was not usable without an interpreter or subject matter expert. Abbreviations indecipherable to non-SMEs. Access to data and tools limited to 2 people because of AutoCAD licensing and know-how. Timeliness. Reliance on those 2 people, the curators, created delays to access and analysis of the data. Mapping workflow was time-consuming. Time lag in updating or recording as constant changes happen in the field. Completeness. Some sections of the garden were poorly surveyed or neglected for more urgent matters because of the mapping workflow. Accuracy. It's really difficult to measure or calculate geometries accurately and with confidence when you've got a CAD file that's not based on a coordinate system. You can't overlay it with other geospatial data sources. And also, the CAD labels and the table information are maintained in 2 different places. Leads to inconsistencies and errors. Plus, at the bottom here, we've got problems for conversion to GIS. Geo-rectified CAD was surprisingly good, but still had locational and scale errors, which are unavoidable. Layers are difficult to separate out into feature classes if they're lumped into one layer, which is the case I had with a lot of base map layers. They were lumped into layer 0. CAD labeling made attribute transfer very difficult. We'll talk about this more in detail later.
By 2015, through a small grant from APGA and ESRI, Huntsville Botanical Garden received a one-year trial copy of ArcMap software and a couple of instruction books. As the assistant curator, I was trying to learn how to use this new technology while continuing to aggressively survey poorly recorded sections of the garden. It quickly became apparent that 1, we needed a GPS unit to increase the speed and accuracy of our surveys and plant inventories, and 2, I needed help to learn how to use ArcMap and develop the GIS workflow at Huntsville Botanical Garden. I began a graduate degree with an emphasis in spatial analysis to gain competency in GIS, and we were able to purchase a Trimble Geo7 through the generosity of the Stanley Smith Horticultural Trust. ESRI introduced the 501c3 licensing, which made the software much more affordable for our nonprofit, but I found that I had little time to implement it as my graduate research workload got heavier. I attended the ESRI UC in 2017 to present a piece of my graduate work, and while there, discovered the Alliance for Public Gardens GIS data model, which would change the way that Huntsville Botanical Garden managed our records.
As we began to plan, we decided to have weekly meetings after work. We determined that the proper data schema was the one that the Alliance for Public Gardens created. It fit our needs perfectly. The feature class names and field definitions are well thought out for the business operations of any public garden. It has predefined relationship classes that are exactly what I would have put together if I were to start from scratch. And it has an online schema dictionary that you can use to determine the proper home for a particular feature you are mapping. We immediately performed a needs and current capabilities assessment, primarily so that I could understand what sorts of problems Tracy and Mike needed to solve. We then prioritized the things that needed to be done first: conversion workflows, preservation of attribute workflows, GPS collection workflows, defining SOPs for data collection and management. As stated earlier, we had accumulated over 30 years of valuable data that we could not lose. There were 149 total layers in our CAD that had cryptic naming conventions that I had to understand, many of which were from temporary projects from years past, and most were irrelevant. One of the problems with this CAD file was that it didn't really follow any defined standards. Layer names were created on a whim and not well thought out. In fact, most of the base map data were all lumped together on layer 0. Georeferencing typically is a two-part process when you're bringing CAD in, but this flowchart, of course, has a little bit more to it. When you're georeferencing CAD, ArcGIS only allows you to use 2 control points, and that gets you into the ballpark. What you'll next need to do is to convert that CAD into a GIS feature class so that you can use more control points for a tighter fit. During compilation, one would typically use CAD as a guide, but the ortho told more truth regarding locational accuracy, and that's what you would usually draw from. In our case, the CAD pavement edges, for example, would remarkably align with the ortho photo after georeferencing. This is a really good indication of how meticulous Mike was in his triangulation and mapping despite his resources at the time. When things aligned, Trace Tool is a very helpful tool here. I was able to compile things like the base map features, boundaries, utilities, plant centers, and areas. There are common problems from the inherent nature of CAD text. In addition to not being georeferenced, as in our case, CAD labels are just text elements, not dynamic attributes attached to the actual feature they're labeling, like GIS. Take a close look at the screenshot of our CAD file. It illustrates the following points. Labels, in our case, were at various sizes, scales, and proximity to the feature that they're labeling. So we couldn't consistently run an automated process like spatial join within a defined distance to reach our ultimate goal of transferring label strings to the appropriate point that they intended to label. Inconsistent abbreviations, or proprietary codes as Tracy called them, had to be deciphered. The labeling was also inconsistent in what taxonomic category was being used. As you look at this graphic, you'll see genus, hybrids, cultivar names, common names, genus, species, or a combination of all of these things. One more thing. If stacked, the labels will create individual unrelated records when brought into GIS as a point feature class. I had thousands of label records that had to be consolidated so that the stacked groupings were one record each. So, as a solution, we came up with a three-phased process. Phase 1 derived a full name from the abbreviation and categorized by taxonomy. Phase 2 consolidate the stacked lines of CAD text to a single record. And then Phase 3 transfer attributes to plant centers and mass planting areas in the final database.
Before adopting GIS, we used a paper form to collect plant change data, when perennial plants were installed or removed, why and where. Compliance in using this form to report changes was poor because it was a hassle for the horticultural staff and volunteers to retrieve the forms and clipboards from across the garden. Often they would plan to complete them at the end of the day, but would subsequently forget to do so, resulting in lost provenance and taxonomy information. Once we launched the Plant Change app using Survey 123, the consistency in reporting information increased. Also, using the Survey 123 application enabled us to multiply the number of collectors to include volunteer groups, since they could use their own devices. This subsequently increased the speed of plant inventories, especially in sections of the garden in which GPS accuracy was less important.
Survey 123 has been a real game changer. Putting together a form is amazingly simple to design and deploy. Shortly after learning myself, I taught Tracy how to create an app in about 10 minutes. The wonderful benefits is that it eliminates the need for paper. It also takes out the bottleneck of data entry. Once the field worker clicks the Submit button, the data is available to see on the map. The curator can then monitor the progress of collection from the dashboard on ArcGIS Online. The only pitfall is that it relies on a mobile device's GPS, which isn't accurate enough for our needs. Accuracy, however, can be enhanced with Bluetooth GPS receivers. That is something we may consider in the future.
With Peter's help, we began publishing web maps using ArcGIS Online, first for internal use to help us locate and diagnose irrigation problems and crowdsource plant change data, and later to develop plant collections-centered app for sharing with the public, which is a preliminary step to getting all of our plant collections accessible online.
I'm Nikki Southers. I'm the Director of Horticulture for the Huntsville Botanical Garden, and I wanted to share some of my experiences with using utility and irrigation web maps. And for years out here, we have all these beautiful things, but we have all these mysteries underground. So we like to dig a lot, and for various reasons. Could be I'm going to plant a plant, or we're going to put in a building, or sometimes it's a post for a fence. And what we need to know is what's under the ground. And so that's what these web maps are able to tell us without going back to the office and shuffling through paperwork to try to find it. Plus, it's information we can easily share with contractors, with other staff. Having the utilities, the electrical especially, it's dangerous for somebody to dig up your electrical lines or stab something into the ground. So it's a safety hazard if we run into those electrical lines. The irrigation is just it's very time consuming. So sometimes with irrigation, we can spend a lot of time trying to find a water leak. So if we have those water lines mapped, then we're able to do that easily. And sometimes it can save us from doing work needlessly. And one example I had, we had water coming up out of the ground, bubbling up, really looked pressurized because we'd had several days of rain. And we looked at the web map and realized that there were no water lines anywhere near the area, and that the problem was just from drainage. If we waited a few days, it would be gone, rather than thinking we needed to turn all of our water off and try to find a leak. We could have spent a whole day on a mystery that just wasn't there, but since we were able to pull up the web map easily, we were able to get that information quickly and make the decision that, hey, we don't have a problem here. So that's just some of the experiences that I've had with using the web map. But I do share the information with other staff because we have solenoids, and a solenoid can get stuck open whenever it's running. So maybe there's a rental event going on and the water went off or decided not to go off, and then we're able to track down that location because the controller's not working and turn off water by a solenoid, thus preventing a very bad wetting situation.
The Public Gardens data model has a dedications table for non-living donations such as structures, benches, statues, bricks, and living memorials like trees and flower beds. The schema also has predefined relationship classes that link the dedication table to a number of feature classes like furniture, structures, artwork, plant centers, and beds. Once that relationship is established, one can look up a dedication and quickly find out what it is and where it is in the garden. Now, think about the heavy burden that a curator already has on his or her shoulders when they are constantly bombarded with interruptions, one of which is locating dedications. Under the established processes, they would have to look up the record in Access and manually search for it in CAD because these two tools are completely disconnected. The bottleneck could be anywhere from a half hour to 2 to 3 hours depending on the curator's knowledge of the dedication. Now that we have these records in the data model, a lookup no longer has to be the curator's responsibility. The decision maker or requester can do it completely on their own without needing to bother the curator at all. Story maps are a beautiful thing for gardens. Here's one for the guests to navigate and virtually tour the grounds. And here's one that showcases one of our newest installments, the Native Plants Teaching Garden.
The Native Plants Teaching Garden is a public space that highlights the way local plants, soil, pollinators, and birds create distinct communities and how they interact to form a diverse, sustainable, and attractive landscape.
In summary, we found that GIS is an incredibly useful tool for a public garden. We had some definite problems that this technology was very good to use to solve. Plus, ESRI's efforts with ArcGIS Online to make these data shareable and accessible to the public is phenomenal. It's so easy to be able to publish something online and be able to make it available to internal entities for staff and management, as well as the public for garden tours. Story maps are beautiful and they're very easy to use.
And the GIS has really helped us share our garden with the world.
I'd like to thank ESRI for allowing us the opportunity to present our findings from the 3.5 to 4 years of work that we've done here at Huntsville Botanical Garden. It's been an absolute pleasure to do this, and we thank you for tuning in.